Good morning. Welcome to episode number 12 of the ZOOMTOWN experiment. For today's experiment and trial run, we're looking at odometry, a methodology where we can track how far a robot, or in our case, a Zoomie, moves or progresses in either the forward or reverse direction. Before we get into the details, let's take a look at what we're going to cover in this video. We'll have a brief explanation of the AS5600 sensor and its applications. We'll look at it at the data sheet and give you an overview of a few critical points on that, and we'll look at some of the features of the sensor. We're going to work on a practical setup where we cover the schematic, or a fritzing diagram in this case, and we'll look at the code to operate this particular sensor. We'll cover it with some practical bench testing so that we can determine if it's suitable for our purposes, and then finally we'll provide an analysis of our findings. Odometry is a key element of autonomous robotics. When the robot is moving, or in our case the Zoomie is moving, we need to keep track of how far it moves. That gives us a rough idea for localization. In other words, so it kind of knows where it's located in the environment. In our case, ZOOMTOWN. Odometry exists on your car. If you drive around a car, it's got an odometer on it, everywhere in the world for that matter. Some places are kilometers, other places are miles. In our case, we're not so concerned about such big distances, but more typically much smaller distances or increments. In our case, it'll probably be, it's America, so I'm probably going to go with inches, but you never know, I might favor the millimeter setting for it as well. But for odometry to work, the principle's rather simple. If you imagine on your car, if everywhere around the circumference of the tire is a mark, and as that tire rotates, when one of those marks touches the surface of the road, you increment a counter. For example, in the case of our cool little tractor here, every time one of those marks hits the bottom, we'll put a mark on a hash table and count up. And we'll go through and repeat that over and over again until it stops. Now, if we know the direction it's moving, forward or reverse, we can determine if we want to count up or count down. That's very simple. Now, most of the time in robotics, you would use what's called a rotary encoder, incremental style rotary encoder. What that means is, as this axle or wheel is moving forward, it's going to count up every single time, and it just keeps counting up to infinity or to the maximum number your microcontroller can handle. This particular unit that we're going to look at is called an absolute encoder, and it's a little bit different than a typical rotary encoder. In fact, it isn't even called an encoder. The official part name for it is a 12-bit programmable contactless potentiometer. Yep, we're going to use a potentiometer as a rotary encoder. The particular unit is the AS5600. I've used this on a couple of other projects in the past, and I'm quite amazed by how good and accurate it is, and reliable. So far, I'm really liking them. Now, what differentiates this one from other types of encoders that you may have seen is it's using a magnet. A very small magnet. It's about 3 millimeters in diameter, maybe even smaller than that, about 1/8 of an inch, and about 1/16 of an inch or 1.5 millimeters in thickness. And we're going to place that at the end of the axle, right in the center of the wheel. And then we'll place this sensor over the top of that. Now, the poles of the magnet aren't in line with the axle or the axes of rotation. Rather, they point outwards or at a right angle to the axes of rotation. With that, the sensor can watch that movement as it rotates and easily determine the rotational position of the axle or our wheel in this case. As long as we count that up, we'll know exactly where we are with a relatively high level of precision. Doing a little quick math, figuring out the circumference of the wheel and dividing that by 4,096 increments, we're dealing with about a 0.001 inch resolution. Way more accurate than we really need, but nonetheless, it could be helpful in some regards. Now let's take a look into the data sheet here a little bit. It's called a 12-bit programmable contactless potentiometer. It measures the absolute angle, that's what I meant by an absolute encoder, of a diametric magnetized on-axis magnet. It's going to use an I2C interface. So as we found on a couple of previous sensors, I'm hoping we can read this very quickly, because if it takes forever to read, it's really useless for our application. There's a number of different settings and so forth. I won't go into the full details of this because I could probably spend about a week talking about it. But I do want to cover a few of the important things that always affect us in our sensors. Operating voltage, it's a 3.3 volt device. Getting the current supply current that it needs is a little tricky on it because it's not constant. You can change states, and depending on what it's doing, it's running a little differently. But for my purposes, I'm going to pick the highest one at 6.5 milliamps. Very, very minimal current. So that's just wonderful there. I'm real happy with that. Okay, right here it kind of shows you how the poles of the magnet are oriented to the sensor. So now you start to get an idea how it can figure out the rotation of the shaft. The red and the green area is the magnet, representing its approximate size. And then, of course, you see the north and south poles. As the wheel rotates, so does the magnet, but the sensor is stationary. So we can read that rotation with the sensor. Here is a close-up view of the module where you can see how the header pins would fit in the back side and then the operating front side of it. Now you can see the chip, and that points towards the wheel in our application. Wiring it up is really kind of simple. You're going to supply 3.3 volts to it. Ground or 0 volts, and that can, in our demonstration here, it's coming right off the PICO. And then we're going to connect SCL over to pin 11 and SDA to pin 10 for our I2C interface. Now let's take a look at it on the bench. I'm going to pull it out with our little test fixture here. As you can see, this is the area where the motor is. This is the back side of the motor. Here's the wheel. And you can almost make out the little magnet right between the sensor and the wheel. And that magnet has probably a gap of about 0.5 millimeter there. And I've had the gap much higher and probably even less at times. It's not real critical for that gap to be a specific value other than probably about 1 millimeter. This will be our standard wheel design that we've been using so far. Now the orientation of this will be in this manner. You would be looking through the top of the Zoomie. This would be the top surface of the Zoomie on the very bottom deck. If I roll it forward, you're looking at it from the front. This is the surface of the wheel, or the area of the wheel that would be touching the ground. So this is the bottom of the Zoomie. And this, of course, is all a crazy-looking 3D printed bracket to hold our little sensor. So with that, I'm going to put that back in the vise, and we will then take a look at the code. Now, the code is also going to include the same code I used to test out our motor and motor drive. So you'll see a lot of extra code in there that we're really not going to pay attention to. We just want to focus on the encoder for today. Now, hopefully this will be big enough for you to see. I'm detailing up above in the comments which sensor we're using, the N20 motor, and the supply voltage to the motor, and making note of the counts per degree, or counts per rotation of 360 degrees. We're going to import a few libraries. Primarily we need I2C, and we're also going to import AS5600, which is a library for this particular sensor. Going to go through, this will be used more for the motor drive. This is setting up I2C on pins 10 and 11 for the AS5600 sensor. This is for controlling the speed of the motor and thus the wheel. And in this area here, we're going to set up our AS5600 sensor, and we need a few variables to keep track of position for us. So we just create a few variables. L_ENC is my object from the AS5600 class, which came from that library we loaded. We're going to scan it, get it all active, and then we're going to take a reading by simply assigning L_ENC dot angle to this variable. That gives us a starting point for our counting, and we'll print that out. Here we're taking a look at a little bit of math we'll need for all of this, because if we're going to convert rotational movement to linear movement, we need to know the circumference of the wheel so that we can perform all the math to go from rotational to linear. You'll see this variable used a lot, CEAP, PEAP, current encoder absolute position, previous encoder absolute position. So that way we can keep track of where it was and where it is. And that comes in real handy when we're handling the 4096 count rollover back to 0, which is what this little function's doing here. We just look at the value. Once it gets to a certain point, we'll add the 4096, and going back the opposite way, and then returning the values for delta distance and delta angle. This function eventually be running in a timer every 20 milliseconds, but before we start it, we do need to get it ready, and then I'll explain the next step here in a second. But here again, we're just reading the angle, getting the delta position or delta distance in both linear and angular by computer underscore delta distance. Here it is right here. And then we're going to move current over into previous so that the next time through this loop it knows what's what. And then we'll take our position or calculate our position by taking current position plus our delta position and print it out. And from there, I'm going to perform a test here, which will determine the duration of time it takes to get a reading. Obviously, we've learned in the past that's very, very critical. So here we're just going to grab the count once and then take a quick nap for 100 milliseconds. Now we will then repeat that read. We're going to set a timer. That'll be running in microseconds, or clock ticks microseconds. ST is our start time. We'll take the reading. We're going to do our conversion, and then reset our variable, and finally we'll record the end time to do these 3 steps, which will have to be performed every time the encoder is read. And we're going to print the start time and end time in case I wanted to monitor it. Then we're going to use the function of time ticks_diff to give me the difference between start time and end time in microseconds. We'll then update our position, print the position, and we'll print the number of microseconds it took to perform these 3 steps of the operation. I'll sleep for 5 seconds so we can read it before all the data goes scrolling by on the screen. Here we're going to start our timer running at a 20 millisecond period, or every 20 milliseconds, and that is the update position guy, which is this, which is reading the sensor. And that'll just keep repeating over and over and over again until we end the program. Here is we're just going to move forward about 2 rotations, and then we'll move in reverse about 2 rotations. Over here on the actual wheel, we got a little red dot there. Hopefully we'll be able to see that as it rotates around twice and then backwards twice. But nothing really fancy here, just setting the velocity at about 60% of total high speed, so this will probably be around 60 RPM. Going forward, this sets the wheel in motion, and we're going to run for 3.46 seconds, which should give us approximately 2 rotations, and then it'll sleep for a little bit before going backwards the exact same amount. After it does that, then the program will shut down. Then after that, it'll set the motor speed duty at 0, clean up the program, print out the current linear distance that it ran, update the position timer by de-initializing it so don't keep running even if the program terminates, and we'll give it 2 seconds to do that before the program completely terminates. We'll go ahead and run our program. Here you can see that it's taking less than 500 microseconds to take a reading. You can see that it's rotating and it's counting up and now counting back down. Cleans up the program and then it terminates it. Let me summarize my findings thus far. Now, of course, I've done more experimenting than what's shown in the video, but I'm quite certain you folks wouldn't want to watch about 3 hours of tests and experiments with this sensor. So let's just take a quick look at what I see with regard to this sensor. It's giving accurate readings. Both in this test and other tests, it does count extremely accurate as long as everything is in place properly. It's easy to use in code. All we do is call the code or call the function, do a little bit of math on it, we've got our position. That's really easy to use. It's efficient to use because the sensor does most of the counting. We don't have to count between 0 and 496. The sensor's keeping track of that part of the count. We're just grabbing that value infrequently and then adding the values to our position. That's a very efficient way of working with a rotary encoder. The time to read is 500 microseconds, or a half a millisecond. Even with 2 sensors, that means it can be read about 1,000 times a second. So I'm really happy with that. It's very compact. It'll be easy to wire up. Here in our test bed, we're using header pins, but that really won't work because this will be the outside edge of the Zoomie. So we'll probably have to solder the wires directly on to that module board. Finally, I'm going to give this a pass. I think we're going to put this in the Zoomies and move forward with this sensor, and I'm not going to bother looking for others in place of it. It's doing what I want. What more can I ask for? For next week's video, we're going to revisit the TCRT5000 photoreflective sensor. I came up with an idea how that might help me for a replacement to my time of flight sensor that was a bit of a disappointment. So I hope to see you during that video, and hopefully we'll have a replacement sensor in place so we can keep marching forward. See you then.